Alright, what's up YouTube? We're back. Um, so today we're going to talk about inverse trig functions, which is kind of a common topic that a lot of first year calculus students kind of have trouble kind of getting a grasp of. And I think that's fair because when I was a first year student, I also had trouble with it, and I think it really stems from a miscommunication from a lot of mathematicians to students. And it stems from this nasty piece of information. So say we have the inverse sine, or the sine to the negative 1 of x, right? So inverse sine x. And so a lot of students are like, great, I know that. We just went over in calculus, sine to the negative 1 means 1 over sine. I think this makes a lot of sense, and we can say, okay, I know that to be, what is it, the cosecant of x, and there's my answer. The inverse sine of x is cosecant of x, and that is factually true. You can say this is the inverse. Sine of the negative 1 is the inverse, as in the inverse is 1 over, and 1 over the sine of x is cosecant x. But when we're talking about inverse trig functions, we don't mean inverse trig like characters. We don't mean like inverse as in 1 over. In this case, we actually mean it as the inverse function, as in if you have f of x equals x squared, the inverse function is f of x to the negative 1 equals plus or minus the square root of x, right? So x squared and the square root of x are inverse functions in the sense that you take the input and you make it the output, and vice versa. You take the output and you make it the input. So what this means, another way of rewriting this is saying the arc sine of x. And in this case, this is a whole different operation than cosecant, cosecant of x. So what I like to do just for future tips is if I mean the arc sine, I will write arc sine, and if I mean cosecant, or 1 over cosine, then I'll just go ahead and write sine to the negative 1. I think it makes a lot of sense when you start doing integrals in calculus. Having different fractions on the top and the bottom, you can powers, and you'll have 2's and negative 2's. I think it's really simple to just keep the positives on the positive exponents on the top and the negative exponents on the bottom, and it makes a lot of sense to me. So with that being said, I'm going to go ahead and switch colors, and we're going to get into a quick example. So first off, let's talk about what we mean when we say the inverse sine. And this works for inverse cosine and also for inverse tangent. So we'll say problem number 1, and it's going to be the inverse sine to the negative 1, as a lot of textbooks will write it. I don't like writing it that way, but that's probably how you'll see it, equals theta. So the first thing I'll do is I'll say, okay, in this section, what they really mean is they really meant to write arc sine of 1/2 equals theta. And what that means is it's not saying like sine. Sine takes a angle and it will give you the ratio of the sides, right? So if I have sine of some value theta, this is the opposite side, we'll call it A. This is the hypotenuse, we'll call it, I don't know, H for hypotenuse. And we know by definition, the sine of theta is equal to A over H. Like by definition, you memorize SOHCAHTOA, you know it for cosine, you know it for tangent. That's what it is. So when I say the arc sine of 1/2, I don't mean, I'm not giving it an angle measure of 1/2. I'm giving it the sides of 1/2. So I'm inputting the ratio of the opposite side to the hypotenuse, and I want to know what this angle here is if I know these two values. I'm going to go ahead and kind of undo my little marks here. So the way I can do this is I can say, and this is probably why the textbooks write it like this, is because it's kind of handy to look at. So I'm going to go back to the inverse sine notation. So sine, I can take the sine of both sides. So taking the sine of the left side, and I can also take the sine of the right side. Now, as long as I take the sine of both sides, it doesn't change the equation in any way. And what I can essentially do is I can just cross out those because they're opposite and they cancel. It's like saying the square root of x squared. It's just x. So that leaves me with 1/2 equals the sine of theta. Right? So 1/2 equals the sine of theta. And we say, okay, well, that doesn't get me anywhere, but really it does, because if we remember our unit circle that we all have memorized, right? That's fun. You should memorize a unit circle. I'm just making fun of people who say memorize it. But you should memorize it. So that means that the sine is the y. So if the sine is 1/2, that means your triangle is going to go over here. Maybe we have this, there. That's your point. Point's right there. And the coordinate point of that is, something, comma, 1/2. And it's going to have some theta, right? So we could do the Pythagorean theorem, right? We know that that's 1. We could figure that out. This ends up being root 3 over 2, but we don't need to know that. So we can just say, you know what? I memorized my unit circle, and I know that the this value, the angle measure for this value is actually just pi over 6, and that is our answer, pi over 6. So essentially what we did in this problem, just a little review, we took the inverse sine, we had the inverse at the very top, line 1, we had the inverse sine of 1/2, which is really, we know means the arc sine of 1/2, but we just said we're going to take the sine of both sides. Sine of inverse sine of 1/2, those cancel, just like x squared, or the square root of x squared, or the cube root of x cubed, those both cancel. And we're left with 1/2 equals, in this line over here, we're left with 1/2 equals the sine of theta. And we drew our little unit circle down here, which we obviously have memorized, of course. You don't need to, you can do the Pythagorean theorem, but you don't need to do that if you haven't memorized. So it's pi over 6. Sweet, that is the first problem down. All right, now we're going to do a little bit more tricky problem, and tricky is red because red is tricky. Oops, not problem 1, we're going to do problem 2. This will be our kind of final kind of tricky example. So let's say we have the sine of the inverse sine of 2, right? So if we have the sine of the inverse sine of 2, what we're saying is kind of what this inner function means is, say we have an angle ratio of 2, and I want to know, right, so this is 2, that's 1, right? I want to know what that angle is, okay? And I want to take that angle and give me the ratio of sides that will make that triangle on the unit circle. But this is a trick question. I said it was a little bit hard. Most students will just try and say, oh, those cancel, and that equals 2, done. But that is wrong, not true. And the reason why it's not true, I'm going to go ahead and go back here. The reason why it's not true is because this term right here, boom, the one I kind of pointed to, that will never actually be anything on the unit circle. If I draw my unit circle here, the max value you can have here is 1. The minimum value here you can have is -1, and you can have 0 in the middle. It says you start from an angle of 0, and you make your way around to pi over 2, or pi. We'll get up to 1. We'll kind of go up to 1. We'll come back down to 0, right? We have 3 pi over 2. We'll make our way to -1, and then back to 0. And then you can go in the other direction. You'll only get between inclusive 1 and -1. Those are the range of values you can get. And so you'll never actually have a triangle that sits on the unit circle, right? On the unit circle, maybe. But you'll never have a triangle that sits on a unit circle that will have an angle ratio, or any of the sides, never will be 2. It has to be between 1 and -1. So the way we actually answer this problem is we say, the sine of the inverse sine of 2 is undefined. Or the way I was taught is you just say, you can say UDF, or UDF to shorten that. Or how I was taught is just an empty set, which is a 0 with a line through it. So there are no solutions. Is kind of the way that gets read. No solutions. Sweet. That's kind of a tricky problem. Most kids just say it's 2 because it's easy to just cancel it out, but you have to kind of look at it a little more deeply and make sure that kind of the domain and range are the same, even though it's kind of tricky. All right, and let's do just a final easy problem. I'll do blue. All right, so let's say problem number 3. Let's say we have the inverse sine of the sine of pi over 2, right? And so we learned from the last one, we have to kind of be careful here, but we do know that the sine of pi over 2, we have a unit circle, the sine of pi over 2 is that theta, it's 90 degrees. The sine of pi over 2 is 1, so we know that that is 1 because it's at the top of the unit circle. So then the inverse sine of 1, it exists. Well, that's just pi over 2. Another way of doing that, like most students love doing, is just saying it's the sine of pi over 2, and those just cancel, and you're left with pi over 2. I can write my pi better. Yeah, so in a little bit of review, we're now at 11 minutes. Let's not squiggle. Yeah, so here is our notes for today. We started off explaining kind of the common problem most kids have with inverse sine because it means two different things. It can mean both at the same time. It can mean this kind of cosecant at the top here. It could also mean arc sine. And that's why I swear by it. I'll always say arc sine if I mean arc sine. And I'll always try and say inverse sine is sine to the negative 1 if I mean cosecant or 1 over sine. Just to clear up the confusion. Let me move into 3 examples. The first example, it was just a pretty simple example. We talked about the unit circle. Having that memorized is super nice. And we talked about how we can just kind of cross these out here. And it gives us, this 1/2 equals sine theta. We go to our unit circle and say, okay, we know that that's 1/2 because sine is the y. 1/2 equals that. So theta must be pi over 6. And pi over 6 is our answer. And then we moved over here and we said, okay, what if we have this value that doesn't exist? It's not on the set of values 1 to -1. Both are inclusive. And then we just say it's undefined, or there are no solutions. You can write it however you want, but it's undefined. And the fourth problem is very simple, kind of like the first problem, except it's a little bit tricky. We kind of did the opposite. So in this problem over here, we took the sine of the inverse sine. Now we're taking the inverse sine of the sine. And really, they do the exact same thing. Those cancel, and you're left with pi over 2. But we just have to be sure that we're checking and making sure that all of the angles and ratios are within reasonable bounds. All right. Thanks for listening. See you next time.